So what is the formula for potassium nitrate? Potassium is K, nitrate is NO3. This one you should remember, this one you can look up. And if you look on, this is group 1 here, potassium happens to be in group 1. So it's got a 1+ valence. And if you remember, nitrate has a 1- valency. Now, if you take the lowest common multiple, it's 1. Therefore, it'll just be KNO3, because they're both 1, and the lowest common multiple is 1, so it's just KNO3. And if you look at it, if you've got the K ion and the NO3 ion, if you put them together, the charge balances out. You get 0. 1 minus 1 gives you 0. Okay? What is the formula for aluminium sulfate? If you look in your periodic table, you've got aluminium as Al, and you've got to remember sulfate from your list of valencies. And aluminium is in group 3, so it's got a valency of +3. And sulfate, as you should remember, has a valency of 2-. Now, if you take the absolute value of each, the lowest common multiple is 6. 3 times 2, which is 6. So therefore, for aluminium, you need the charge of aluminium. Because of the valency, to get 6, you need to multiply the number of aluminiums by 2. And for SO4, you need to multiply by 3, and you'll get 6. And so you'll have, for every molecule of aluminium sulfate, you'll have 2 aluminium atoms and 3 sulfate ions. So that's how we do that. And what is the valency of M in the compound MO4 2-? So this sort of manganate ion, what is the valency of M? So if we go in our periodic table, the valency of oxygen is usually 2-. Okay? If there are 4 of them, the valence or the charge of 4 oxygen atoms becomes -8. Now, if the ion has an overall charge of 2-, then the valence of M must add with the valence of O4 to equal 2-, right? So if you've got 8 negative charges, and in total, what you can see from the outside is 2 negative charges, there has to be some number of positive charges cancelling out some of these negative charges. So the valence M plus the valence O4 has to equal 2-. So the valence M plus 8- equals 2-. And so the valence of M must be 6, plus 6. Let's have a look. M plus 6, O4 -8, and if you do the maths, you'll get -2. Write down the formula for Dinitrogenpentoxide. Okay, so this is quite a complex one, but you just break it down into steps. Di is 2, fairly straightforward. So dinitrogen is N2. Di is 2, dinitrogen would be N2. Now, obviously by the same logic, pent is 5. Oxide is O, so it's O5. And so you put them together now, and you get N2O5. Okay? So it's very straightforward, and it all comes from the name. You can see it straight away. And that's the beauty of this chemical naming convention, that everything you need to know is already in the name. So what does the chemical formula represent for a covalent network substance, and why is it written this way? So we did a lot on covalent molecular substances, CO2, O2, H2O, all of these things. But they exist as discrete molecules. So, you know, a carbon dioxide molecule could be flying around by itself, and another carbon dioxide molecule could be going by itself in any direction that you want. They're not interacting with each other in any way. But in a covalent network substance, like silicon dioxide, they're actually all interlinked together. So then, how do you write that chemical equation? Do I write, for instance, for 1 mole of silicon dioxide, do I write Si 6.022 times 10 to the 23 O 12.044 times 10 to the 23? Okay, like that's essentially the same thing as what we were writing before, the number of molecules and things inside. But is this a really clever way of doing it, or is it just tedious? And in my opinion, it's really tedious. You can't write that and expect everyone to know what you're talking about. So the way we write it is, the chemical formula of a covalent network substance is the smallest repeating unit of the covalent network structure. And what I mean by a repeating unit is, if there's a silicon and then an oxygen and then a silicon and then another oxygen, then silicon and oxygen is the repeating unit. So that's what we write, SiO. Similar to ionic compounds, it is essentially the empirical formula for the substance. So in ionic compounds, the same thing happens. You get sodium, then chlorine, then sodium, then chlorine, then sodium. So you just write sodium and chlorine together, rather than writing a billion different Na and Cl. You just write one. So it's the same thing with covalent network structures. This formula is used because the crystal will likely have an innumerable amount of atoms, and it would be impractical to write all of them, particularly if they have a repeating pattern. So it'd be silly to write a billion different chemicals, or a billion of the same chemical over and over and over again, simply to represent a repeating pattern anyway. So we just write it as a single repeating unit, and that's all. And that tells chemists everything they need to know. So there's like an implied convention. That's why we write covalent network structures the way we do. So that wraps up today's lesson on formulae for compounds. So we actually looked at how we write formulae and how we name chemical compounds. So in future lessons, we'll be looking at other ways of identifying compounds. And so I look forward to seeing you at our next lesson.